Testing, can you hear me? I accidentally started the stream with the ending stream title. Okay, so my stream is public now. Hold on. Right. Hold on a minute. I don't exactly need like full screen browser. I'm just shortening the browser. Okay. So I'm going to be reading University Physics, Volume 1. I finished mechanics. Well, I finished reading mechanics. Not all of mechanics. I think up till applications of Newton's laws, and I was in work in kinetic energy. Okay. This entire book is just 2 units. Mm, Chapter 7, Introduction. Hold on. Uh, I just need to get something done. All right. In this chapter, we discuss some basic physical concept involved in every physical motion in the universe, going beyond the concepts of force and motion and change in motion. All right, let's just go to the next chapter. Work. In physics, work is done on an object when energy is transferred to the object. In other words, work is done when a force acts on something that undergoes a displacement from one position to another. Forces can vary as a function of position, and displacements can be along various paths between 2 points. We first define increment of work done by force acting through infinite, infinitesimal displacement as the dot product of these two vectors. So the change in work is force times the change in displacement. Then we can add up the contributions of our infinitesimal displacements along a path between two positions to get the total work. The vectors involved in the definition of work done by a force acting on a particle are illustrated in figure 7.1. While in general, equation 7.2 requires mathematics beyond the scope of this text, in many simple situations like integral becomes a familiar integral in one variable. We will examine several such examples and restrict our discussion to these cases. We choose to express the dot product in terms of the magnitudes of the vector and the cosine of the angle between them. Because the meaning of the dot product for work can be put into words more directly in terms of the magnitudes and angles. We could equally well have expressed the dot products in terms of the various components introduced in vectors. In two dimensions, these were the x and y components in Cartesian coordinates or the r and phi components on polar coordinates. In three dimensions, it was just x, y, and z, which choice is more convenient depends on the situation. Because of the magnitude of force times the cosine of the angle the force makes with the given direction is the component of the force in the given direction. Components of a vector can be positive, negative, or zero depending on whether the angle between the vector and component direction is between 0 and 90 degrees or 90 and 180 degrees or is equal to 90. The units of work are units of force multiplied by the units of length, which in the SI system in newtons times meter is newtons times meter. This combination is called a joule for historical reasons that we will mention later and is abbreviated as J, the English system. Still used in the US, the unit of force is the pound and the unit of distance is the foot. So the unit of work is foot pound. Work done by constant forces and contact forces. Simplest work to evaluate is that done by a force that is constant in magnitude and direction. In this case, we can factor out the force. The remaining integral is just a total displacement which only depends on the endpoints A and B, but not on the path between them. Um, so force F times from A to B dr. This force is a constant, right? But it's only constant in one direction, right? So the magnitude and direction of the force is constant throughout the entire path of A and B. And RB minus RB. So this is only possible if the direction was the same. RB minus RA. Oh, no, no, no. Sorry. It's constant force dot product RB minus RA. And then we take to this. Because 7.3a shows a person exerting a constant force F along the handle of a lawnmower, which makes an angle theta with the horizontal. The horizontal displacement of the lawnmower over which the force acts is t. Or what if the velocity is constant because the friction and the force this guy is pushing on? They cancel out, so the velocity of the lawnmower is constant. So do we only consider the force from the person or do we consider the net force? So when we are talking about the work done on the lawnmower by the man, you only consider the force pushed by the man, right? And not any other. The work done on the lawnmower is WFD or FD cos theta. Scalar value of f, scalar value of t times cos theta, which the figure also illustrates as the horizontal component of the force times the magnitude of the displacement. Figure 73, figure 7.3b shows a person holding a briefcase. Person must exert an upward force equal in magnitude to the weight of the briefcase, but this force does no work. Causes displacement over which it acts is zero. Because 1.3c, where the person in B is walking horizontally with constant speed, the work done by the person on the briefcase is still zero. But now the angle between the force exerted and the displacement is 90 degrees. And cos 90 is zero. So this upward force is doing no work when it comes to pushing this back horizontally. Calculate the work you do to push a lawnmower. How much work is done on the lawnmower by the person in figure 7.3 if he exerts a constant force of 75 newtons at an angle of 35 degrees below the horizontal and pushes the lawnmower 25 meters on ground level? Hold on. Let me open Desmos. So wait, let me log in as well. So hold on. And I should open my website as well. It should be no grid. And then what do we need? Force. Seven point one. 75 newtons. The angle is 35 degrees. Is the lawnmower 35 degrees and pushes the lawnmower 25 meters. 25 meters. So constant force 75 degrees. No, force downwards is 35 degrees. So, right, this is the horizontal and 25 Newton, 75 newtons. So cos 75 will give me the force in the horizontal direction. And I have to multiply all this with 25. And what do I get? 75 cos 35 uh, 25. And this cos, is it in radians? Should be in degrees. We have 1535 in two significant figures. Does this count for significant figures? I'm guessing it does, right? Two significant figures, it would be 1500 joules. One, no, wait. Okay, they're putting three significant figures. 1.54 times 10 to the power 3 joules. When you mow the grass, other forces act on the lawnmower besides the force you exert, namely the contact force of the ground and the gravitational force of the earth. Let's consider the work done by these forces in general. For an object moving on a surface, a displacement r is tangent to the surface. The part of the contact force on the object that is perpendicular to the surface is the normal force. Same thing for the weight as well, right? Um, However, if the object is more than a particle and has internal structure, the normal contact force can do work on it. For example, by displacing or deforming its shape. This will be mentioned in the next chapter. The part of the contact force on the object that is parallel to the surface is friction. For this object sliding along the surface, kinetic friction is opposite to dr relative to the surface. So the work done by the kinetic friction is negative. If the magnitude of Fk is constant, as it would be if all other forces on the object were constant, then the work done by friction is minus Fk, where LAB is the path length on the surface. The force of static friction does not work in the reference frame because between two surfaces because there is never displacement between the surfaces. All right. You decide to move your couch to a new position on your horizontal living room floor. The normal force on the couch is 1 kilonewtons, and the coefficient of friction is 0.6 newtons. Uh, let's see. Okay. Normal force on the couch is 1 kilonewton. This is the couch from the side. 1 kilo thousand newton. Coefficient of friction is 0.6. You first push the couch 3 meters parallel to the wall. Okay, you push it in that. So the coefficient of friction is over there. You move it 3 meters and then 1 meter. 3 meters parallel to a wall and then 1 meter perpendicular to the wall. Here. How much work is done by the friction force? By the frictional force. So the normal force does no work. The friction force, however, so it's work one is 3 times 0.6. They're in the same direction. 3 times 0.6, 1.8 joules. And then 1 times 0.6 is 0.6 joules. Work here, work here. So the frictional force does, so then this becomes 2.4 joules. Why do we say negative? Work is a scalar, right? It's not, what does negative work mean? Okay, negative 2.4 k joules. Why k? Coefficient of friction is 0.6. Do they mean 0.6 k? Do they mean this? Then it would make sense. You don't like the new position, so you move the couch straight back to its original position. What was the total work done against friction? So 3 square plus 1 square, which is 3 square is 9, 1 square is 1. So we have 10. This length over here is root 10. So work done, the third work done is root 10, 0.6. This is in kilo. Square root 10. 1.8, 1.9 kilojoules. And I got that wrong. How though? Oh, we add 1.9 to 2.6. 2.4, I mean. 1.9 plus 2.4 is 4.3. Yeah. Work done by forces that vary. In general, forces may vary in magnitude and direction at points in space. The path and paths between 2 points may be curved. The infinitesimal work done by a variable force can be expressed in terms of the component of the force and the displacement along the path. So work done by a variable force over a curved path. An object moves along a parabolic path y is equal to 0.5 meters uh, times it by x squared. Or because of x squared, there's meter to the power of 9 minus 1. From origin A 0, to the point B 2, 2. Under the action of a force 5 Newton meter y at 10 newtons per meter in the j direction. Calculate the work done. Force is constant, right? No, it's not. plus 10x. If we just consider the, uh, so let's say let me think. This is what? 7.4. Work is A to B. From A to B, force times it by TR. 0.5 x square. Force is 5y plus 10x. Do we consider work in the x direction and then work in the y direction? So throughout this path, there was work in the x direction. The x direction, it was from 0 to 2. We have 10x dx. No, no, no. Five x square. We have 5 times 4 is 20. And then 0 doesn't count. And then in the y direction, we have 5y. Should I write dx? 5, 0 point, so half x square dx. 2.5 to x square dx. Cube 2, 0. We have 2.5. We have 8. 2.5. 6.666. So, um, Let me see. I got that completely wrong. 5y 0.5x squared, 5y and 10. We have half x squared, 2.5x squared, x cube over 3. We have this. Okay, I was wrong apparently. The infinitesimal element of work is f of x dx and f of y dy. So 5y dx plus 10x dy. Then we have 5 this dx. Wait a minute. This I over here is in the x direction. Should be 5y the x direction and then 10x in the this direction. Yeah, I got confused. But let me try doing all this again. So 5y times it by dx. 5 this is the same thing as before. Joules. But in the y direction, we have 10x dy. 10 instead of x, we have 2y root 2y. Y minus half. No, no. 3 over 2. 3 over 2. You can take this 3 over 2 out. I will just write 30. 30 over 2 root 2. And then we have 2 to the power of 3 over 2, 60, which is way too high. Is there a division by 2 that I'm missing? No, I got this wrong. When I took 3 over 2 out, it should be 2 divided by 2 divided by should be like this 20 over 30. 20 over 3, I mean. Now we have 26.66666. You have this 33 point. So work total is 6.6. Uh, However, they wanted in 2 significant figures. They didn't really. I'm assuming they're giving us the exact number. But if this method is wrong, just let me know. I don't want to end up learning the wrong thing. One very important and widely applicable variable force is the force exerted by a perfectly elastic spring. It satisfies Hooke's law. F is equal to minus k delta x, where k is the spring constant. Delta x is x minus x. What is this? Equal? Equilibrium. Is the displacement from the spring's unstretched equilibrium position. Note that the unstretched position is only the same as the equilibrium position if no other forces are acting on it. Forces between molecules or in system undergoing small displacement from a stable equilibrium behave approximately like a spring force. Calculate the work done by a spring force. We can choose the x-axis along this length of the spring in the direction of increasing length. As in figure 7.7 with the origin at the equilibrium position, equilibrium is equal to 0. The positive x corresponds to a stretch and negative x to a compression. With this choice of coordinates, the spring force has only an x component. F of x is equal to minus kx, and the work done in exchanges from xa to xb is um okay, minus half k x square b minus xab. Notice that WAB depends on the starting and ending points AB and is independent of the actual path between them. As long as it starts at A and ends at B, that is the actual path involved going back and forth before ending. Another interesting thing to notice about equation 7.5 is that for this one-dimensional case, you can readily see the correspondence between work done by a force and the area under the curve of the force versus its displacement. Recall that in general, one-dimensional integral is the limit of the sum of infinitesimals, representing the area of stripes, as shown in figure 7.8 and shown in figure 7.8. Since f is equal to minus kx as a straight line with slope minus k, when plotted versus x, the area under the line is the algebraic combination of triangle areas, where areas above the x-axis are positive and those below are negative. Okay, so we are left with half times space times height. The height is minus kx and the base is x. The height is, yeah, whatever. Hold on a minute. Since x squared at b position minus x. Radius is just one half of triangle's base along the x-axis times the triangle height along the force. Showing areas under the line between XA and XB. It's not triangle, it's this entire thing. More like trapezium. When XA is negative, the total area under the graph for the integral is the sum of the positive and negative triangular areas. When XA is positive, the total area under the curve is the difference between two negative triangles. Wait a minute. We have, let's say this. XA. I should just write it like this. Or should I write B on the other end? So I'm stretching the spring that direction from XB to XA. Force is equal to minus kx. work done is force times the x, and that means work done from A to B. Is the starting point B or A? It's A. So the integral of force x at position A minus at position B. Wait, why is it reversed? Sorry. B, A. But now for the area of this, it's like it's trapezium, so F at XA plus F at XB divided by 2. Times it by the height, XB minus XA. So this plus this divided by 2 times this. That's the area of a trapezium. Now what? Now we have by the definition we have this, this, yeah. We have A plus B. And then we have, so this times this would be B squared. A times B will cancel out with B times A. Then we are left with A times A. And that's the equation we derived. Kinetic energy is plausible to suppose that the greater the velocity of a body, the greater effect it could have on other bodies. This does not depend on the direction of the velocity, only its magnitude. At the end of the 17th century, a quantity was introduced into mechanics to explain collisions between two perfectly elastic bodies, in which one body makes a head-on collision with an identical body at rest. First body stops, the second body moves on with the initial velocity of the first body. The idea behind this quantity was related to the forces acting on the body and was referred to as the energy of motion. Later on, during the 18th century, the name kinetic energy was given to the energy of motion. With this history in mind, we can now state the classical definition of kinetic energy. And when we say classical, we mean non-relativistic. That is, at speeds much less than the speed of light. At speeds comparable to speeds of light, the theory of relativity requires a different expression for kinetic energy of a particle. Since objects or systems of interest vary in complexity, we first define the kinetic energy of a particle with mass m. K is equal to half mv square. We then extend this definition to any system of particles by adding up kinetic energies of all constituent particles. We have K is equal to mv squared. So the sum of this is the total kinetic energy. You can rewrite this in terms of p squared over 2m. The units of kinetic energy are mass times the square of speed. The units of force are mass times acceleration. So the units of kinetic energy are also units of force times distance, which are the units of work or joules. You will see in the next section that work and kinetic energy have the same units because they are different forms of the same more general physical property. What is the kinetic energy of an 80, 80 kilogram athlete running at 10 meters per second? So mass is 80 and then velocity is 10 meters per second. We just do half mv square and we get the kinetic energy. Because velocity is a relative quantity, you can see that the value of the kinetic energy must depend on your frame of reference. You can generally choose a frame of reference that is suited to the purpose of your analysis and that simplifies your calculations. One such frame of reference is the one in which the observations of the system are made. Another choice is a frame that is attached to or moves with the system, likely an internal frame. The equations of relative motion discussed in this. Okay. Kinetic energy of a particle is a single quantity, but the kinetic energy of a system of particles can be divided into various types, depending on the system and motion and its motion. For example, if all the particles in a system have the same velocity, the system is undergoing translation motion and has translation kinetic energy. Uh, okay. A player lobs a midcourt pass with 624-gram basketball, which covers 15 meters in 2 seconds. What is the basketball's horizontal translation kinetic energy while in flight? So we just plug in the speed 15 meters in 2 seconds, so half m v square. An average molecule of air in the basketball in part A has mass 29 micrograms and an average speed of 500 meters per second relative to the basketball. There are about 3 times 10 to the power 23 molecules inside it moving in random directions. When the ball is properly inflated, what is the average translation kinetic energy of the random motion of molecules inside relative to the basketball? So half m times v square. There are about these many. Average speed is this. Average mass is this. So half mv square, this already gives the average kinetic energy, right? The average is this m v square, and the total is this. We just multiply the number of molecules. How fast would the basketball have to travel relative to the court as in part A, so as to have the kinetic energy equal to the amount in part B? We're talking to this much amount, or this much. So velocity, or they're still using the this kinetic energy formula, half mv square, but it's rearranged to get the speed. Yeah. Uh, we have discussed how to find work done on a particle by forces that act on it, and how is that work manifested in the motion of a particle according to Newton's second law. The sum of all those forces acting on a particle, net, or the net force, determines the rate of change in momentum of the particle or its motion. Therefore, we should consider the work done by all the forces acting on a particle or the net force to see what effect it has on the particle's motion. Let's start by looking at the net work done on a particle as it moves through over an infinitesimal displacement, which has the dot product of the net force and displacement. Newton's second law tells us that F net is equal to m times acceleration, and the work done is m times the acceleration times change in displacement. So we have m v times dv. Wait, wait a minute. So mass times velocity time dot product with change in velocity. Wait, can you do that? Can you just pass the dt over there? Where we substituted the velocity for the time derivative of the displacement and used the commutative property of dot product. Since derivative and integral are scalar, are since derivatives and integrals of scalars are probably more familiar to you at this point, we express the dot products in terms of Cartesian coordinate before we integrate between any points A and B on the particle's trajectory. This gives us the net work done on the particle. So we have work done, net AB. We have this. Is the velocity, no wait, we have dv. Is the velocity constant? No, that doesn't make sense. So we have change in work done is the mass times the velocity at that point times the instantaneous change in v. Sorry, times the instantaneous change in, yeah, times the instantaneous change in velocity. No, wait, this is not instantaneous change. This is infinitesimal, right? Infinitesimal velocity. In the middle step, we use the fact that square of velocity is the sum. In the middle step, we use the fact that the square of the velocity is the sum of the square of its Cartesian products. In the last step, we use the definition of a particle's kinetic energy. The important result is called the work energy theorem. we get this around the net work done on a particle is this. According to this theorem, when an object slows down, its final kinetic energy is less than its initial kinetic energy. The change in its kinetic energy is negative, and so the net work done on it, and so is the net work done on it. If an object speeds up, the net work done on it is positive. When calculating net work, you must include all forces that act on an object. If you leave out any forces that act on an object, or if you include any forces that don't act on it, you'll get a wrong result. The importance of the work energy theorem and the further generalization to which it leads is that it makes some types of calculations much simpler to accomplish than they would be by trying to solve Newton's second law. For example, in Newton's laws of motion, we found that the speed of an object sliding down on a frictional plane by solving Newton's second law for the acceleration and using kinematic equations for constant acceleration, obtaining final velocity v square is u square plus 2as. And we have sine theta over here. It s is the displacement down the plane. Which direction is this velocity in? We can also get this result from the work energy theorem. Since only two forces are acting on an object, gravity and the normal force, and the normal force doesn't do any work, the net work is just the work done by gravity. The work dW is the dot product of the force of the gravity and the displacement. After taking the dot product and integrating from an initial position to a final position, one finds that the net work as this mgyf minus yi. When the y is positive up, the work energy theorem says this equals the change in kinetic energy. Using the right angle triangle, we see that wf minus wi is equal to sine f minus sine I sine theta. Wait. Going down a ramp, so let's say this is S initial, S final, or this is also Y. Well, in this direction it's Y initial, Y final. This sine theta. So G is downwards. G is in that direction. Velocity F and velocity I, these are also in the down direction, right? Velocity F is in that direction, right? And same for velocity I. This is what's getting me confused. What is gained by using the work energy theorem? The answer is that for a frictionless plane surface, not much. However, Newton's second law is easy to solve only for this particular case, whereas work energy theorem gives final speed for any shaped frictionless surface. For an arbitrary curved surface, the normal force is not constant, and Newton's second law may be difficult or impossible to solve analytically. Constant or not for motion along a surface, the normal force never does any work because it's perpendicular to displacement. A calculation using work energy theorem avoids this difficulty and applies to more general situations. How much is depth? Okay, I will just read this chapter and then I will end the stream. The concept of work involves force and displacement. The work energy theorem relates the net work done on a body to the difference in its kinetic energy, calculated between 2 points on its trajectory. We express the relationship between work done and the time interval involved in doing it by introducing the concept of power. Since work can vary as a function of time, we define the average power as the work done during a time interval divided by the interval. Then we can define the instantaneous power. Power is dw over dt. If the power during the interval varies with time, then the work done is the time integral of the power. So one work done is 1 joules per second. Uh, Power is joules per second is 1 watt. No, wait, work done is measured in joules. Joules per second is measured in watts. 1 joules per second is 1 watt. Another common unit for expressing the power capability of everyday devices is horsepower. 1 horsepower is 746 watts. 746 joules per second. Power involved in moving a body can also be expressed in terms of the force acting on it. If a force F acts on a body that is displaced R in time dt, the power expended by the force is dw over dt. Force F. Force F is constant times dr. Okay, they're treating force as constant. Yeah, force times velocity, where v is the velocity of the object. The fact that the limits implied by the derivatives exist for the motion of a real body justifies the rearrangement of the infinitesimal. All right, then. I will. I wanted to do the next chapter as well. I'll end the stream here, and yeah, I will study the next chapter next stream. Anyways, see you guys next time. Bye.